Okay, we have good morning to everyone. So we have started already the signed binary numbers, and we have uh, mm, discussed how to represent a negative number uh, in a binary system. So there are three ways to represent a negative number. One is signed magnitude representation, signed ones complement representation, and signed twos complement representation. Okay, so what we have done, we have actually considered number 9. We have considered number 9, and this number represented, we have represented 9 with 8 bits, and the binary representation of 9 is 1001, and because we are using 8 bits, so I will put 4 zeros after that, before 1001. So this is the 8-bit representation of 9, or you can say it is a 8-bit representation of plus 9. So 00001001, it can be represented as 9 for unsigned binary, or it can be represented as plus 9 for signed binary. Now, this we have already studied. Now I will show you what is the difference between the signed magnitude ones complement and twos complement. Okay, same thing I will write here. Signed magnitude ones complement and twos complement. So what I will do over here, I will show you how to represent a positive number and negative number with these three techniques. So suppose we are going to represent plus 9 and plus 9 for the signed magnitude, ones complement and twos complement. So for this three technique, the representation of plus 9 will be identical. That will be nothing but 1001, and you will put 4 zeros before that. The same thing happened with ones complement representation, and same thing happened with twos complement representation. So the positive number representation in signed magnitude, ones complement and twos complement will be identical. But in case of minus 9, what will happen? You will have the 9 as 1001, and the extreme leftmost bit will be represented by 1 because it is minus 9. So you have 0, 0, 0, and it will be 1. Because all we know, this bit is 0, it means it denotes the positive sign, and the extreme leftmost bit is 1, it means it denotes the negative sign. So this is the representation of minus 9 in the signed magnitude case. Okay, and the rest of the bit is actually representing the magnitude that we already studied. In case of ones complement, how to represent minus 9? You will do the ones complement including the sign bit. How could you represent plus 9? You actually represent the plus 9 like this: 0, 0, 0, 0, 1, 0, 1, where this leftmost bit 0 is actually indicating the plus sign. Now in case of ones complement representation of the plus 9, what you have to do? You have to exchange all the zeros or replace all the zeros with 1 and all the ones with zeros, including the sign bit. So what will happen? This extreme left bit is actually represent the sign. So this will be changed to 1 also. And this at the extreme left position, if 1 is present, then this 1 will represent the negative sign. And then you have 111, 0, 1, 1, 0. So you will replace zeros with 1 and ones with zeros, and also the sign bit will be complemented. So here it should be 1, 1, 1, 1, 0, 1, 1, 0. So this is the ones complement representation of the -9. And the third case, how could you represent -9? Same thing you have to do. You have to do the 2's complement of the magnitude as well as the sign bit. The extreme leftmost position is the sign bit. Okay, so what you have, we understand, or if you again see that +9 is represented by 8-bit representation, 0, 0, 0, 0, 1, 0, 0, 1. So for 2's complement, representation of -9, what to do? You have to represent the magnitude as well as the sign. What is the sign bit? The extreme leftmost position. This is the sign bit. Plus sign is actually representing because 0 is there. So you will go for 2's complement representation. So magnitude and sign, all bits will be represented in 2's complement. So first we will go for the 1's complement, 1, 1, 1, 1, 0, 1, 1, 0, and then you will add 1. So finally you will have 1, 1, 1, 1, 0, 1, 1. So that we will write 1, 1, 1, 1, 0, 1, 1. So you see, if you have a positive number, suppose +9, then for signed magnitude, 1's complement and 2's complement, the representation of the +9 is identical. No change is there. But the same negative number -9 can be represented in 3 different ways. In the signed magnitude case, the representation is 1, 0, 0, 1, 0, 0, 1. In the 1's complement, the representation process is 1, 1, 1, 1, 0, 1, 1, 0. And for the 2's complement, the -9 represented as 1, 1, 1, 1, 0, 1, 1. So for the 1's and 2's complement, what we are doing, we are representing the magnitude as well as the sign bit by the help of 1's complement or 2's complement. Okay. Now the arithmetic addition. The addition of two numbers in a signed magnitude system follows the rule of ordinary arithmetic. If the signs are the same, we add two magnitudes and give the sum common sign. If the signs are different, we subtract the smaller magnitude from the larger and give the result the sign of the larger magnitude. Example, suppose we have +25. We are adding +25 with -37. Actually, what we are doing, 37 is larger, so we are going to subtract the smaller magnitude from the larger magnitude, and we will put the sign of larger magnitude in front of the result. So here we are subtracting 25 from 37, and because you see in front of 37 there is a negative sign, so I will put negative sign in front of result. So finally I will get -12. A very basic thing. In class 3-4 you are doing these things, and it is done by subtracting the smaller magnitude 25 from the larger, that is 37, and using the sign of 37 for the sign of the result. This is a process that requires the comparison of signs and the magnitudes and then performing either addition or subtraction. Yes, obviously it is quite true. So first you have to check the signs, you have to check the magnitude, and then you will decide what you need to do. You need to do the subtraction or addition. Okay, because if you have +25 minus of minus 37. So what you will do? Will you do subtraction? No, you will actually do the addition. If you do if you have minus 25, then minus of minus 37. So what you will do? You will actually subtract 25 from 37. Now, if you have 25 plus of minus 37, so you check the signs. So automatically what you will do? You will actually subtract 25 from 37. And because negative sign present in front of the larger number, so you will put negative sign in front of the result. So first you have to compare the sign and magnitude, then you will decide whether you have to do the addition or subtraction. It is for the general mathematics. But the same procedure applies to the binary numbers in the signed magnitude system. Same procedure applies to the binary numbers in the signed magnitude system. Okay. In contrast, the signed complement system does not require a comparison or subtraction, but only addition. So this is the main advantage. In the previous cases, in the normal arithmetic addition or subtraction, what we have to do, we have to compare the signs as well as the magnitude, and then we have to decide whether we will do the addition or subtraction. Same thing happened for the signed magnitude system. But when we are dealing with the digital computers, we are not going with this the comparison system. We don't need to check the signs as well as the magnitudes of the two numbers. Or we don't need to do the subtraction. What we need to do? The addition. Because already we have studied that when we have studied the binary subtraction using the ones and twos complement, we have understood that instead of doing the subtraction, it is much more easier to do the addition. So when we are adding the two binary number, we are actually eliminating the complexity associated with the subtraction operation. Because in case of when we are dealing with digital computers, we need to eliminate the complexity associated with the subtraction. Because in general, for the binary subtraction, we need to borrow from the next higher position if the subtrahend is less than minuend. So that is complex process. So that is why we are going for the addition. Same thing over here. If we follow the signed complement system, in the signed complement system, we will do only the addition. We don't need to compare or subtract. The addition of the two signed binary numbers with negative numbers represented in signed twos complement form is obtained from the addition of the two numbers, including their sign bits. Okay. So it is, we are talking about the addition of the two signed binary numbers, okay, with the negative numbers represented in signed twos complement form is obtained from the addition of the two numbers, including their sign bits. The carry out of the sign bit position is discarded. So some examples already given. So first we will consider the positive number +6 and +13. So only the addition operation going on. So okay. So +6 and +13. So 6, we are representing 6 with 8 bits. So we have 0, 1, 1, 0. This is the 6. And then 0, 0, 0, 0. 13 means 1, 1, 0, 1. And then we have 4 zeros. So we will add these two. 1, 1, 0. Then 0, then 1, 0, 0, 0. So this gives you the +19 because At the leftmost position, you have a 0, and 0 denotes the positive sign. So this is plus 19. Now after that, minus 6 plus 13. You see, negative numbers must be initially in the 2's complement, and that the sum obtained after the addition, if negative, is in the 2's complement form. Okay, means what it does mean, if you see this example, here you have minus 6 and plus 13. If minus 6, if the negative number is in the 2's complement form, and if you add these two, minus 6 and 13, if you add these two, where minus 6 represented in 2's complement, and after the addition, if the result is negative, the result will be automatically in the 2's complement form. Okay, so I will show you the two examples, and you can understand what is happening. So minus 6, right now you have minus 6. So the minus 6 will be represented in the 2's complement form. So what is plus 6? 0, 0, 0, 0, 0, 1, 1, 0. Now how to represent minus 6 in the 2's complement? First go with the 1's complement, 1, 1, 1, 1, 1, 0, 0, 1, and then you add plus 1. So you will have 0, 1, then 0, 1, 1, 1, 1, 1. Okay. So you have 1, 1, 1, 1, 1, 0, 1. And you have plus 13, right? 1, 1, 0, 1, 0, 0, 0, 0. Now just add. You have 1, you have 1, you have 1, then you have 0, then 1 carry, again 0, then again 0, then again 0, then again 0, and you have 1 carry. So this is the carry. And here it is written, you see, and carry out of the sign bit position is discarded. So what I will do, I will discard this carry, and finally result is 1, 1, 1, 0, 0, 0, 0, 0. Okay. So this gives what? This gives you plus 7. Because here, if you observe very carefully, when you will add these two numbers, minus 6 and plus 13, if you do the arithmetic operation, if you follow the rule of arithmetic addition, you will automatically get the plus 7. Okay, and also I am getting the plus 7 from here. Minus 6 is represented in the 2's complement form. We are adding these two, but the result actually positive. So I am getting directly this result. Okay. Now if the case is reversed, so what will happen? Suppose you have suppose you have plus 6 and minus 13. The plus 6 represented 0, 1, 1, 0, 0, 0, 0, 0. And minus 13 represented with 2's complement form, right? So what about plus 13? 1, 1, 0, 1, 0, 0, 0, 0. And what about minus 13 in 2's complement form? 1, 1, 1, 1, 0, 0, 1, 0, and then you add plus 1. So you have 1, 1, 0, 0, 1, 1, 1, 1. So this is the 2's complement. So you put it right here, 1, 1, 1, 1, 0, 0, 1, 1. Now add these two. You have 1, then you have 0, then you have 0, then you have 1, then 1, 1, 1, 1. Now you see, normally what happened when you will add these two numbers plus 6 and minus 13, you will get the result will be minus. Okay. Now here minus 13 represented in the 2's complement form, and the result what you obtain, that is also the negative number. So this number automatically, this number automatically in 2's complement form. So this is the 2's complement of minus 7. Okay. So if we just see what is the result when you are doing plus 6 minus 13, you will get minus 7, or in binary, when we have plus 6 and minus 13, the result is actually 1 1 1 1 1 1 1 1 1 0 0 1. So this is the 2's complement representation of minus 7, and it can be proved because you see, this is what, this is the plus 7. So how could you represent minus 7 in 2's complement? So first you will replace all the zeros and ones with 1 and 0 respectively. So you will have 1 1 1 1, then 1 0 0, and then you add 1 over here. So what you will have, 1 1 1 1 1 0 0 1. So this is the 2's complement of minus 7. So you see, after this addition, where the negative number represented in the 2's complement format, and when you are adding this two number, the result will be the negative number. So that negative number automatically represented in the 2's complement form, right? Now if you have minus 16 minus 13, then also what you will do, you will add these two. So minus 6 also represented in 2's complement form, minus 13 represented in 2's complement form. So you see, minus 6, already we have minus 6, right? Minus 6 is 1 1 1 1 1 0 1 0, 1 1 1 1 1 0 1 0, and minus 13 is 1 1 1 1 1 1 1 1 0 0 1 1 1 1 1. Now you add, you have 1, then 0, then 1, then 1, 0, 1, 1, 1. I think 1 will be there. So this is the carry. So you discard this carry. Finally, the result is 1 1 1 0 1 1 0 1. So this result is nothing but minus 19 in 2's complement form. Okay, minus 19 in 2's complement form. You see, 1 1 1 0 1 1 0 1, 1 1 1 0 1 1 0 1. Okay. So in this way, we will do the subtraction operation. So in each of the 4 cases, the operation performed is addition with the sign bit included. We have already done. Any carry out of the sign bit position is discarded, and the negative results are automatically in the 2's complement form. We have seen, to determine the value of negative number when in signed 2's complement, it is necessary to convert it to a positive number to place it in a more familiar form. So this is the important part. So Okay, so you see, one question can arise in your mind that when we are representing -9 with the ones complement or twos complement, suppose the -9 suppose this -9 is represented like first it will be 0 sorry 1 1 1 1 1 0 0 1, so 0 1 1 0 then 1. This is the twos complement representation of -9. So here I am defining that -9 equal to this. But if someone asks that in the signed twos complement system, the binary number is given as 1 1 1 1 0 1 1. So what is the value? What is the value? Only this thing is given. And it is mentioned it is the signed twos complement system. Now find out what is the value of this. Okay. Now how to find out? So when you are seeing that at the leftmost position you have 1, so it should be a negative number. Right. Now what you will do, whatever number is given to you and it is written it is in the signed twos complement system, so again do the twos complement of this binary number including the sign bit. Okay, so what you will have, you have 1 1 1 1 1 1 1 1 0 1 1, right? So go for twos complement with the sign. So what you have, 0 0 0 0 1 0 0 plus 1. So you have 0 0 0 0 1 0 0 1. So what it gives? This gives you +9. But you see at the leftmost position you had a 1 which represents the negative sign. So your result will be, or your answer will be -9, because when this number is given to you, it is represented in the signed twos complement system, and at the leftmost position you are seeing that there is a negative sign. Sorry, at the leftmost position you are seeing that there is a 1, so it means it is a negative number. So how to find out the exact value? Because it is represented in the signed twos complement form, you will again do the twos complement of this given number. So you will get this +9. But if you write only +9, then the answer is wrong, because at the leftmost position there was a 1. So it gives you the negative sign. So you have to write -9. Right. So this thing also represented over here. Suppose the signed binary number 1111 1001 is negative because the leftmost bit is 1. Now the twos complement of this number, its twos complement 0 0 0 0 then 0 1 1, which is equivalent to +7. But because there is a 1 at the leftmost position, that is why the correct answer will be -7. Okay. So tell me, do you have any doubt on this? Is that okay?
Yes, sir.
Okay. Now, arithmetic subtraction of two binary numbers when negative number are in 2's complement form is very simple and can be stated as follows. Now take the 2's complement of subtrahend including the sign bit and add it to the minuend. The same thing. Whatever we have studied in the previous cases, we have studied the binary subtraction using the 2's complement. But here, in the previous cases, we had the unsigned numbers, but right now we have the signed binary system. Okay, so here we are going to subtract two binary numbers when negative numbers are in the 2's complement form. So take the 2's complement of the subtrahend including the sign bit and add it to the minuend. A carry out of the sign bit position is discarded. This procedure occurs because a subtraction operation can be changed to an addition operation if the sign of subtrahend is changed. Like this is the minuend and this is the subtrahend. So you see plus minus a, minus of plus a. So it can easily be changed that plus minus. So you can add minus b. Like this, already we have done these things. You see. Okay, so what can be done? Suppose it is written plus minus a plus of minus b. So when it can be written like this, plus minus a minus b, or minus a minus b, where a is 6, b is 30, and both represented in the 2's complement form, and we have added these two, and finally the result whatever we have obtained, it is also in the 2's complement form, isn't it? You have already done it. Okay, so we had minus 6 and minus 13, so it can be represented as a and represented as b. Okay, or you can represent it as minus a and minus b. So these two numbers represented in the 2's complement form, we have added these two numbers, and the result whatever we are obtaining after the addition, that is also in the 2's complement form, because the result is also a negative number. That is why it is automatically in the 2's complement form. But when you have done this thing, minus 6 plus 13, you have represented minus 6 in the 2's complement form. But when you added these two, the result was positive 7. When the result is positive, then it will be in its original form. Already we have seen this. Here you see minus 6 represented in the 2's complement form, and plus 13 represented means normally. It is the normal binary representation, 8-bit representation of plus 13. 13 means 1101, and for the 8-bit representation, we have put 4 zeros before 1101. And when you are adding these two, where this negative number represented in the 2's complement form, so after addition, you see you are obtaining 0, 0, 0, 0, 0, 111. And also, if you observe minus 6 plus 13, the result will be plus 7. So when the result is positive number, after this addition of these two binary numbers, you will get the result in its original form. So this number 0, 0, 0, 0, 0, 111 is actually gives you plus 7. So it is not in the 2's complement form, right? It is in the original from by seeing this value, you can easily detect what is the equivalent decimal number. But in this case, when you have minus 13 and minus 13 represented in 2's complement form, and when you add these two binary number, you can understand your result will be negative, and that negative result will be automatically represented in 2's complement form. So this 1111 1001 is actually 2's complement representation of -7. So when the result is minus, it will be automatically in the 2's complement format, because this negative number represented in the 2's complement format. So when the result is negative, the result will be automatically in the 2's complement format. But when the result is positive, it is not in the 2's complement format. By observing the result, you can easily detect what will be the equivalent decimal number. Okay. So you see plus minus a minus of plus b, it can be changed to plus minus a plus of minus b, or plus minus a minus of minus b, so it can be changed to plus minus a plus of plus b. So means so by, you see, in both the cases you had the negative numbers. In both the cases you had the negative number, means there was a subtraction actually. In both the cases, you need to do the subtraction, but that subtraction is changed to the addition. You see, in the second case, automatically you have minus sign and minus sign over here, so it will be a positive sign. So right now it is converted to the addition, and you see here is a minus sign present and plus sign present. So you can also means what you can do when you have plus 13 minus of plus 6. So it is actually what? 13 minus 6. So plus 13, or also you can add minus 6 with plus 13. In this way, this is the another representation way. Okay. So subtraction operation converted to the addition operation. In the first case, we are doing addition with minus b, and the second case we are doing addition with plus b. Okay. That is actually happening in the 2's complement system, in the digital computers. We are not exactly doing the subtraction. What we are doing the addition. In the first case, we are doing addition with minus b. In the second case, we are doing addition with plus b. Right? Changing a positive number to a negative number by taking its 2's complement. Okay, it is very easy to understand. Okay. So consider the subtraction minus 6 minus of minus 13. Okay, so it gives you plus 7. Now in binary with 8 bits, this is written as, so this is actually minus 6, this is actually minus 13, both represented in the 2's complement form, and in between there is a minus sign, right? Minus 6 represented in 2's complement form, minus 13 also represented in 2's complement form, but in between there is a negative sign, because we are actually doing the subtraction. The subtraction changed to addition by taking 2's complement of subtrahend minus 13 to give plus 13. Okay, so you see what is happening over here. Okay, I'll write here. It's very easy to understand. So first you had minus 6, and then you had minus 13, and in between In between means there is a subtraction operation. -6 minus -30. So -6 represented in 2's complement form. So that is actually 1 1 1 1 1 0 1 0. -13 represented is also in 2's complement form. That is 1 1 1 1. Then 0 0 0 1 1. 0 0 1. So this is the 2's complement of -13. This is the 2's complement of -6. And actually what we are doing? We are doing the subtraction. That is why minus sign is present. But actually what is happening? Minus sign, -6 minus of -13. So we can easily write -6 plus 13. Okay. -6 plus 13. So when -13 converted into the +13, so what I will do? I will take again the 2's complement of this. If I take 2's complement of this quantity, 2's complement of this quantity, it will give you the +13. So 2's complement means 0 0 0 0 1 1 0 1. Hello? Hello? एक मिनट, मैं दो मिनट बाद फोन कर रहा हूँ, मैं एक मीटिंग में हूँ, फोन कर रहा हूँ. Okay, so because it is converted to the +13, so how could you get the +13? You just do the 2's complement of this number and this gives you the +13. This is the +13 because in the leftmost position right now 0 is present. It means it gives you the positive sign. So this is the +13. So finally what you are doing? You are actually doing in this way -13 -6 +13. So +13 means 0 0 0 0 1 1 0 1 and -6 means 1 1 1 1 and it will be 1 0 1 0. +13 0 0 0 0 1 1 0 1 -6 means 1 1 1 1 1 0 1 0 1 0 1 0. Then just do the addition. You have 1 1 1, then 0, then again you 0 0 0 0, again 1. So this is the carry bit. You just discarded this bit and this gives you the result, which is 0 0 0 0 1 1 1. So this is the +7. From here also you can get the +7. So when the result is +7, it will be in its original form, not in the complemented form. Okay, but if the result is negative, then it will be in its 2's complement form. When the result is positive, it will be in its original form. By observing this binary number, you can easily detect what is the result, +7. But if the result is -7, then the result will be in its 2's complement form. Okay. So, and from that 2's complement form, what you have to do? You have to do again the 2's complement to extract the exact value. Already I have told you. Okay. So I have told you this way. In the sign 2's complement system, when the number is given like this 1 1 1 1 0 1 1, and if you see that extreme leftmost bit is 1, so number will be negative. So what will be the exact value? What we have done, we have obtained the 2's complement of this number and 2's complement is nothing but 00001,001. So the number is +9. But you have to check whatever binary number is given to you, at the leftmost position, a 1 is present. So that is why number is negative. So you have to write -9. Okay. So this is all about the arithmetic subtraction of the signed binary system. So what we are doing actually, we are actually adding two numbers. The main thing is that what is the advantage? We are not doing subtraction. We are not comparing sign. We are not comparing magnitude. We are actually doing the addition. Okay. For in the digital computer, we cannot afford the subtraction. We are actually doing the addition for the simplicity. If you have a negative number, you will represent that negative number in the 2's complement form, and then you will add. If the result is negative, then it will be automatically in the 2's complement form. If the result is positive, then it will be in its original binary form. Okay. Now, binary codes. The binary codes play an important role in digital computer. The codes must be in binary because computers can only hold ones or zeros. A bit, by definition, a binary digit. When used in conjunction with binary code, it is better to think of it as denoting a binary quantity equal to 0 and 1. Now, binary codes can be classified as numeric codes and alphanumeric codes. Numeric codes are codes which represents numeric information, that is only numbers, as a series of zeros and ones. 8421, XS3, gray code are the numeric codes. Numeric codes used to represent the decimal digits are called binary coded decimal, BCD codes. Numeric codes used to represent the decimal digits are called the binary coded decimal. That is 8421, 2421, 5211 are the BCD codes. I will tell you what is 8421. These are the weights. Okay. Alphanumeric codes are codes which represent alphanumeric information. That is letters of the alphabet and decimal numbers as a sequence of zeros and ones. FCD and ASCII code are the alphanumeric codes. We are very comfortable with decimal number system, but digital system force us to use the binary system. Although the binary number system has many practical advantages and is widely used in digital computers, in many cases it is very convenient to work with decimal numbers, especially when communication between man and machine is extensive. Since most of the numerical data generated by man are in decimal numbers, to simplify the communication process between the man and machine, several systems of numeric codes have been devised to represent decimal numbers as a series of BCD codes. Okay, so mainly the decimal number here, we are actually going to code the decimal number in binary. Okay, because in practice we are dealing with the decimal numbers, but in case of computers, digital computers, the computer always deal with the binary system, either ones and zeros. Okay, so we already know what is the binary representation of the decimal digits 0 to 9. Okay, and then when we have a binary decimal numbers, also we know how to convert a decimal number into the binary. All those things we know, but it is one kind of coding technique. Binary coded decimal. Here we are going to code the decimal digits in binary system. Okay. A BCD code is one in which the digits of a decimal number are encoded one at a time into groups of 4 binary digits. It's very much important. So BCD is what? BCD code is one in which the digits of decimal, you need to remember this thing, digits of decimal number. Digits means 0 to 9 only. Decimal digits are only from 0 to 9. 10, 11, 12, 13, 14, 15, 16, 100, 200, those are decimal numbers, not the digits. Digits are only 0 to 9. So BCD is what? By help of the BCD, we are going to code the decimal digits into a groups of 4 binary digits. These codes combine the features of decimal and binary numbers. There are a large number of BCD codes. In order to represent decimal digits 0 to 9, it is necessary to use a sequence of at least 4 binary digits. Such a sequence of binary digits which represents the decimal digit is called a code word. Okay. Such a sequence of binary digits which represents a decimal digit is called the code word. All BCD codes have at least 6 unassigned code words. That is also important. Now, to represent a group of 2 to the power n distinct elements in a binary code requires a minimum of n bits. Yes, it is very much true. So, means what it does mean, suppose you are representing 0, 0, 0, 1, 1, 0, 1, 1, and you are representing 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. So you see here, how many symbols are there? 4 symbols. And here 8 symbols are there. So for 4 symbols, how many bits you are using? 2 bits. For 8 symbols, how many bits you are using? 3 bits. So here small n is equal to 2, and when you have 2 bits, you can represent 2 to the power n, that is 2 squared, that is 4 symbols or 4 binary numbers. And here when small n is equal to 3, so 2 to the power n is 2 cube, that is 8 symbols or 8 binary sequence you can represent. You see, a group of 4 distinct quantities can be represented by 2-bit code 0, 0, 0, 1, 1, 0, 1, 1. A group of 8 elements require a 3-bit code with each element, sorry, these are simply 0, 0, 0, 0, 0, 1, this one. Okay, so just give me one moment. These examples show that the distinct bit combination of n-bit code can be found by counting in binary from 0 to 2 to the power n minus 1. Obviously, how to? 0 to 2 to the power n minus 1. Means for this case, it should be 0 to 3, and for this case, it is 0 to 7, isn't it? Because 0, 0 means 0, 0, 1 means 1, 1, 0 means 2, 1, 1 means 3. Same here. This is 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that point is valid. These examples show that the distinct bit combination of n-bit code can be found by counting in binary from 0 to 2 to the power n minus 1. That also satisfied from here. That can also be seen from here. Okay, so I'll stop here. We will continue in discussing the BCD coding from the next class. Any doubt you have, whatever I have told you. If you have any doubt, you can mail me or you can WhatsApp me. I will answer.